two particles is interesting in many cases, but in order to see what really is happening and how much structure, you have to go to more than two particles. Two particles is a little too special. So we need to go beyond two particles and see what happens with these operators. So I'll do that. So we'll add more particles. So let's do that. So if you have n particles, capital N, we can consider also permutations. And how many permutations are you going to have? You're going to have n factorial permutations. In notation of Hilbert space, n factorial permutation operators. So why is n factorial? Because a permutation is a reordering of your n objects. And therefore, in order to define a reordering, you must decide which object is going to be the new first. You have your n objects there, so you have n choices to pick a first, and n minus 1 choices to pick a second, n minus 2. So n factorial is the number of permutations. The permutations form a group. So the permutations of n objects form the symmetric group. S capital N with n factorial elements. Just like you study the group SU2 of 2 by 2 unitary matrices, or the group SO3 of three-dimensional rotations in space, the permutation group is a group that deserves a lot of study. It's a finite, discrete group. It's not a continuous group of transformations. It's discrete transformations, and they do funny things. So we need to understand this group. So let's describe the notation of what is a permutation. Suppose you have n equal 4 particles. So a given state is represented by A, B, C, D. And you could say this is the first particle, second, third, and fourth. And these are the states. And now we're going to write the perturbation. The best thing, I think, is just do an example. P3, 1, 4, 2. So a permutation now has capital N labels, so 4 labels. And this is a permutation acting on this state. Remember the 2-1 permutation exchange, the state in 2 was put in 1, the state in 1 was put in 2. Here is the instruction. The instruction is put in position 1 the third state. So here it says 3, so the third state goes into the first position. So that's the first position. The first state goes into the second position. The fourth state goes into the third position, the third index here. So the third position is now occupied by the fourth state, D. And the second state goes into the fourth position, E. So this is the way we are going to define permutations. People define them in different ways, and you have to be sure you know what it means. But I'll write this. This means put third object in first position. Here, the second one, let's write put first object in second position. So it's nice to have this notation because now you can understand how the group works. A group of transformations is a set of elements that can be multiplied. There is an identity, and things have inverses as well. So permutations have inverses. If you rearrange the objects in one way, you can rearrange them back. So for example, what would be the inverse of this permutation? I would try to figure out what is the inverse of P3142. So I look at this thing and I think of what is the instruction that I must put in order to rearrange back this series. And I say, well, I must put the second back in position 1. So there should be a P2 here. I should put the fourth in position 2. And then I should put the first in position 3. First in position 3. And I should put the third in position 4. So I claim that is the inverse of this operator. P213 is the inverse of this is. So you can check it again. P2413 times P3142. You just do it on A, B, C, D. Well, the first one you already know is 2413 is put the third in 1, put the first in 2, put the fourth in 3, and put the second in fourth, B. And then it says put the second first, so that's an A, put the fourth second, B, put the first third, C, and put the third fourth, D. So it's back to the original one. So indeed, it is the inverse. So you can write your permutations and play with them and figure out how to multiply any two permutations. More generally, we write the permutation as follows. Suppose you have, more generally, a permutation is written with some index alpha, collective index alpha, that says how the integers 1 up to n are rearranged into alpha of 1, alpha of 2, up to alpha of n. So think of a permutation and taking n integers and rearranging them. So the first one, the new first index is going to be alpha of 1, alpha of 2. And alpha is a rule that takes the n integers from 1 to n and reshuffles them. So if you have a state, so this is a simple thing, because then if you have a p alpha, this alpha means really P alpha 1, alpha 2, all these things, P alpha 1, alpha 2, alpha 3, alpha 4. If those act on U1, 1, U2, 2, up to UN, capital N, N, what does it give you? Well, it says here that you should put the one that has alpha 1 here on the first position. So you should put first the U alpha 1. And then you should put next the U alpha 2. And all the way up to the U alpha N. That's, in formulas, the rule that I was giving you above there. It tells you how to move the states from one to the other. You see, if alpha 1 was 3, it would correspond to take the state U3 and putting it first. So it's like that. So whatever alpha 1 is, whatever number, that state must be pulled into the first ket. Okay, so let's just think a little about an example, because it starts getting interesting. So let's do 3 particles for a little while, just to see what it is. So 3 particles, n equals 3. So what are the permutation operators? You would say P1, 2, 3 is what? Put the first particle first, the second particle second, the third particle third. Doesn't do anything. That is the identity. So that's the identity element. But then you could cycle them, P3, 2, 1, P2, 3, 1. These are 2 more elements. This should have 6 elements because it's 3 factorial. And now you have the following one, P1, 3, 2, for example. That was not in the list. You had the P1, 2, 3, and now you flip this 2, P1, 3, 2. If I cycle them, P3, 2, 1, and P2, 1, 3, these are it. The middle one, 3, 1, 2. Yes. I was supposed to be cycling them. 3, 1, 2. And 2, 3, 1, yes. Otherwise, I would have repeated that. Good eye. Okay, so these are our operators. And these ones are kind of funny. They're simpler ones. Please look at them. This operator says put the first particle in the first position. So the first particle is left unchanged. The 3 and 2 are permuted. So people sometimes write this. They say this permutation operator is just a single transposition, 3, 2, or 2, 3. these two are transposed, and the first is left invariant. So this can be written as a single transposition. In this permutation operator, the 2 is left invariant. The second state is copied to the second position. But the 1 and 3 are exchanged. So this is a transposition of 1 and 3. And in this last permutation operator, the third state is left invariant on the third position. Nevertheless, the second is put in first, and the first is put in second, so it's a 1-2 transposition. Okay? So the group has broken into things that are transpositions and slightly more complicated things. Now let's look at the transpositions. So these are transpositions. Transpositions. Okay. What about the transpositions? Transpositions are like the permutation operators we were doing before of two particles. You're just changing two particles. You're leaving the other ones unchanged. So these transpositions are Hermitian and unitary. Positions are Hermitian. And unitary, just like we had P21 before. Now, here comes the first statement that is quite remarkable about this permutation group. Any permutation, now we claim, is the product of some transpositions. You see, if somebody gives you a permutation of n integers, I think you're convinced that by changing 2 at a time, you can reach that. So that means that with transpositions, you can reach every possible element. So any, this is very important, any permutation is the product of transpositions. And that implies, in a sense, the main result that you want from operators in this Hilbert space. Since transpositions are unitary and any permutation is a product of transpositions, any permutation is unitary. So all permutations are unitary. It's not true that all permutations are Hermitian. You see, when you have the product of Hermitian operators, the product of Hermitian operators is not necessarily Hermitian. You've seen that. If you have two operators that are Hermitian, the order changes, and the product is not Hermitian. X and P, Hermitian operators, the product is not Hermitian. So all permutations are unitary, but are not Hermitian. And the third concept that comes here, illustrated all in S3, is also a very fundamental concept. We said that any permutation is a product of transpositions. But it's not a unique product of transposition. In fact, you could, if you are given some order of objects and you're asked to rearrange them by transposition, you may do them in different order. So the product is not uniquely determined. the product is in fact, you could find somebody that does a permutation with some number of transpositions and another person with another set of transpositions. But one thing that has to happen, and it's always the same, is that the number of transpositions is the same mod 2. That is, if you find that to get a permutation you need an even number of transpositions, everybody else will need also an even number of transpositions. If you find an odd number of transpositions, everybody will find an odd number of transpositions. And that's kind of clear if you've achieved the desired order by doing some number of transpositions. You can add 2 more transpositions and not change anything. You can flip 2 objects and flip them back. So this is a pretty important result as well. So it means that permutations are either even or are odd. So permutations are even if built with an even number of transpositions, and are or odd if built with an odd number of transpositions. So 2 kinds of permutations, even permutations or odd permutations. So all these things we've kind of seen with this permutation group. There's one more thing that is necessary to note. Something that may have seemed a coincidence there. In fact, the 3 on the right are transpositions, and they're a single transposition each. So each one of those on the right is an odd permutation. It's built with 1 transposition. On the other hand, the other ones are even transpositions, the first 3. The first one is built with 0 transpositions, but the others are built with 2 transpositions. It's something you could just see in detail. In fact, I would say it's worth doing the table of multiplication of this group. But that coincidence is in fact true. In Sn, in the group Sn, the number of even permutations is equal to the number of odd permutations. It's a pretty nice result. There's equal numbers of even and odd permutations in any permutation group. Actually, it's surprisingly simple to show that. You think of the even permutations here. Here are the even permutations. And here are the odd permutations. And you can easily show that there's equal number on this one. So let's do it. One way is to take the permutation element. So suppose you have a permutation, how should I call it? P21. you leave everything the same, but you have P21. That permutes the second and first labels. Since it's an N group, the rest are left invariant, so 3, 4, 5, 6, 7, 8, 9, 10. And you say this maps any permutation here into a permutation there. Why? Because if you have an even permutation here, any element here has an even number of transmutations, of transpositions. So this is another transposition. It transposes 2 and 1. So when you multiply an element here by P21, if it has an even number of transpositions, now it has an odd one. So it must land somewhere here. So this P21 maps the even permutations to the odd permutations. Moreover, it maps them in what's called one-to-one fashion. If you have 2 permutations here that are different, it will map to 2 permutations here that are different. Why? Because suppose you have here Pi and Pj, 2 permutations. One is mapped to P21 Pi, and the other is mapped to P21 Pj. But if Pi and Pj are different, 2 permutations here, I and j, Pi and Pj, and if they are different, then it follows that these 2 are different as well after you multiply them by P21. Why? Because if they were equal, P21 has an inverse, is itself P21, so you could multiply them in, and then you would show that Pi is equal to Pj, and that can't happen. So 2 different elements here will go to 2 different elements there. So if you think of all your elements here, if you have 20 elements here, they go to 20 elements here. The only thing that can happen is that some elements are not reached here. That would mean that these 2 sets are not the same. So you need to show that this map reaches everybody. So this shows it's a one-to-one map. And in fact, it's kind of a joke, but in a way to think of this, 1-to-1 really means 2-to-2, in the sense that 2 things go to 2 things. So it's kind of a funny name, 1-to-1. So the other thing is that you need to show that everybody reaches. So the map is called surjective. Everybody reaches. So it's clear that everybody reaches because if you have a pk in here, a permutation pk, this pk can be written as p21 times p21 times pk, because p21 times p21 is 1. And this pk, since this was an odd permutation, this is an even one. And then you've shown that pk is obtained by acting with p21 on some even permutation. So you reach. So the map is surjective. And therefore, these 2 things are the same. They're identical numbers of even and odd permutations. A very nice fact about these groups.